Hi again. Today I would like to show you how to use DLD-VISU to design a combinatorial circuit. You log in and go to the menu and select combinatorial logic design, which has mainly 4 steps. You can enter your function as a Boolean function or as a truth table. The Boolean function can be in standard form, canonical form, or non-standard form. The standard form can be CNF or DNF, and you have an example here to see how to edit your function. So if you select the truth table, you can adjust the number of variables, and then you can switch click on the line to switch the value between 0 and 1 and x don't care. If we have this selection, we can go to the next step and select one of 2 approaches to minimize the function. For instance, the K-map. Going to the next step, a subchart appears which shows the steps required to minimize the function according to the K-map approach. And the first step in this subchart is to set up the K-map, which is already done by DLD-VISU. The next step is to find all the prime implicants. You have here the possibility to assess yourself by editing these prime implicants. Let's try some. B, C, D prime and A, B, C, and press the next step. Okay, as you can see, we edited 2 prime implicants correctly, and the third one is wrong, and we have one missing. DLD-VISU finds the correct ones, and with color mapping to the K-map. So the core prime implicants is finding them is the next step, and here again we can either try it or just click on the next step. So and as you can see, one of these prime implicants is not a core implicant, and so the minimized function would be this one here. That is the last step in the minimization. We can return to the main chart or to the main steps and select the logic style. We can select between logic gates, multiplexers, decoders, lookup tables. Let's take the logic gates. You can implement the circuit with AND or with NAND only or NOR only. And let's take the NAND version because it is more complicated than the AND OR version, and select the number of the inputs of the gates and go to the next step. You will see that the implementation with NAND is a little more complex than with AND and OR only. So it consists of 4 steps again, and the first step is to do the implementation with AND and OR gates only. So if we have this, we replace each of these gates by its NAND equivalent, as you can see here. This is, for instance, the equivalent of this AND term, and this is the OR equivalent, the NAND equivalent of the OR gate. So the next step is to identify the redundant inverters. So these two inverters are successive, so they don't make any sense. The same applies to these inverters and to these pair also. So in the last step, we just remove these inverters from the circuit, and we have the final circuit.